So yesterday's lesson, we ended by talking about resonance structures, and what resonance structures are, just to kind of review, is they are the same chemical formula, but can be for one particular compound, but it can be drawn in a couple of different ways. Oftentimes, that means that same chemical structure might have, or that same chemical formula might have a double bond or a triple bond in it, and the double bond or triple bond might move that location. Now, the issue is that not every single one of those atoms or of those drawings is the best possible drawing. Okay. And there is a way for us to figure out what the best possible drawing is. And the way that we do that is with something called formal charge. Formal charge is a mechanism, or it's a bookkeeping scenario that chemists put into play to allow us to identify what the best, most stable arrangement of atoms are and electrons are in that particular molecule. And the actual formula for doing it is, like, for calculating formal charge, is really quite simple, but it's not an actual charge. So once we've calculated the charge of, or the formal charge of a molecule, we're not actually saying that molecule has a 0 charge or a -1 charge. What we're saying is that is the preferred structure over the other resonance structures that could potentially exist. The best possible structure would have a formal charge of 0. So if the formal charge equals 0, what that means, where every atom in the compound has a formal charge of 0, then that's going to definitely be the preferred structure. However, that's not always the case. Sometimes you might do the math associated with it, with that particular molecule, and find out that the best possible formal charge might be a -1. And I'm going to try to explain what that means in a moment. But there is a math formula associated with formal charge, and that math formula associated with formal charge is really difficult and complicated. Its formal charge is equal to valence electrons minus number of non-bonding electrons, or in our world, we just might say number of dots, minus number of bonds to that atom. So a formal charge it looks at one atom at a time, and it says how many valence electrons does that atom bring to the table, how many dots are on that one, how many electrons are on that atom, and then how many bonds is it participating in. So again, in terms of our example, formal charge, valence electrons minus number of dots minus number of bonds. So here's two molecules that are really, really quite similar. In theory, there would probably be another version of this where the double bond would be between the other chlorine and carbon. But for sake of argument, I didn't want to go too overboard here. So I'm just going to simply calculate the formal charge for each atom in the molecule. And so I'm going to start with the one on the left-hand side. And I'm going to start with oxygen and then go to chlorine, carbon, and chlorine. So my formal charge, so for oxygen, my formal charge is oxygen, according to the periodic table, has 6 valence electrons, minus, in this case, oxygen has 4 dots, so 4 electrons, minus the number of bonds. In this case, oxygen is participating in 2 bonds, so 2 bonds. So oxygen's formal charge would be 6 minus 4, which is 2, minus 2, which is 0. So oxygen's formal charge is 0. I'm going to do the same thing for the chlorine on the left. Chlorine's formal charge, well, chlorine has 7 valence electrons. The chlorine on the left is participating in has 6 dots around it, so 6 electrons. And it's participating in 1 bond, so it has 1 bond. So 7 minus 6 is 1, minus 1 is 0, so chlorine's formal charge is equal to 0. Yes?
Will it ever be a negative number?
It can be.
What happens then?
I'll show you in about 2 minutes. Now, the next one we're going to do is carbon. So I'm going to do carbon. So carbon's formal charge. Carbon brings 4 valence electrons. Carbon has 0 dots, so 0 electrons. And it's participating in 1, 2, 3, 4 bonds, so 4 bonds. So carbon's formal charge here is 4 minus 0 minus 4. It's going to be 0. And lastly, the right-hand chlorine. So we have chlorine, formal charge, 7 valence electrons, minus, in this case, 6 dots, so 6 electrons, minus bonds, in this case, is 1 bond. 7 minus 6 is 1, minus 1 is 0, so chlorine's formal charge is 0. So for this atom, for this molecule, I have 0 plus 0 plus 0 plus 0 equals 0. And that's going to become important in a minute. In the molecule on the right, okay, I'm going to start with oxygen, go to the chlorine on the left-hand side, do carbon, and then do chlorine, the same pattern. So the formal charge for oxygen is going to be 6 valence electrons minus 6 dots, so 6 electrons, minus 1 bond. So in that case, oxygen's formal charge would be 6 minus 6 is 0, minus 1 is a minus 1. I'm going to shift to the chlorine on the right-hand side, the left-hand side. So that chlorine formal charge is, chlorine brings 7 valence electrons to the situation. It has 4 dots, so 4 electrons, and it's participating in 2 bonds. So 7 minus 4 is 3, minus 2 is minus 1, right? So chlorine's formal charge here is minus 1. Going to shift to the bottom here where I'm going to do carbon. So carbon's formal charge has 4 valence electrons minus 0 dots, so 0 electrons, minus 4 bonds. So in this case, carbon's formal charge is equal to 0. And then lastly, the chlorine on the right. Chlorine's formal charge, it brings 7 valence electrons to the table, minus 6 dots, so 6 electrons, minus 1 bond. 7 minus 6 is 1, minus 1 is 0, so that chlorine has a formal charge equal to 0. So when I add up this molecule's formal charge, it's minus 1 plus minus 1 plus 0, plus 0 plus 0. Wait, did I do that right? What did I do wrong here? 6 minus 6, that makes sense, and 7 minus 4 is 3. Yeah, I guess I did that right. Did I do that right? Did that math add up? Something seems off. Hold on. Let me check my math.
First chlorine has a formal charge of 1.
Plus, because, yeah. The first chlorine should be a plus 1. Because I can add. Thank you for catching that. Woo! All right, so in any case, let's fix that. So in this case, I knew something looked wrong. Negative 1 plus 1 is 0, plus 0 plus 0 is also 0. Now, how do we know which structure is the better charge? Or is the better structure? In this case, the one on the left is going to be considered our preferred structure. So the one on the left is our preferred structure because each atom in the molecule's formal charge is 0. Okay, so even though both structures' total formal charge is 0, because the one on the left has 0 for carbon, 0 for oxygen, 0 for chlorine, and 0 for chlorine, that means it's the most preferred structure. Does that make a little bit of sense? All right, so formal charge, right, is valence electrons minus number of dots minus number of bonds. Okay, we got one more example, so we'll go through it. This one is a little bit less work. There's less things going on here. So I'm going to go from left to right, oxygen, carbon, oxygen. So in the case of the first one, oxygen, formal charge, oxygen is 6 valence electrons minus the dots, which in this case is 6 electrons, minus the bonds, which is 1 bond. So if I can do the math here correctly, 6 minus 6 is 0, minus 1 is minus 1. Carbon has 4 valence electrons, minus the dots, which in this case is 0 dots, so 0 electrons, minus the bonds 2, 4, 6, 8, which is not 2, 4, 6, 8, which is 4 bonds, so 4 bonds tells me that carbon's formal charge will be 4 minus 4, which is 0. Now the oxygen on the right side, formal charge of oxygen is, let's see, oxygen brings 6 valence electrons, minus the dots, which is 2 electrons, minus the bonds, which is 3 bonds. 6 minus 2 is 4, minus 3 is a plus 1, right? Yeah, plus 1. Yeah, whew. Oxygen is, formal charge here is a plus 1. So here we would do negative 1 plus 0 plus 1 is equal to 0. We're going to do the same set of the same situation on the right-hand side. So here I'm going to take oxygen's formal charge going from left to right is oxygen has 6 valence electrons minus the dots, which is 4 electrons, minus the bonds, which is 2 bonds. 6 minus 4 is 2. Minus 2 is 0. So oxygen's formal charge is 0. Moving along to the carbon. Carbon's formal charge, in this case, carbon has 4 valence electrons, minus the dots, which is 0 electrons, minus the bonds, which is 4 bonds. So carbon's formal charge in this case is going to be 0. 4 minus 4. Lastly, the oxygen on the right-hand side. Oxygen has 6 valence electrons, minus the dots, which is 4 dots, so 4 electrons, minus the bonds, which is 2 bonds. So oxygen's formal charge here is 6 minus 4, which is 2, minus 2, which is 0. So here we have a 0 plus a 0 plus a 0 equals a 0. So in this instance, the preferred structure is going to be the one on the right. Is going to be the one on the right because all of the atoms have a formal charge of 0. Does that make a little bit of sense?
Is there going to be a way that like both of the structures that you give us would both be 0 and you have to figure it out from there, or no?
So the question is, if I gave you 2 structures and they both added up to 0 in terms of the total formal charge, would we have to figure it out? No, I don't think I would give you one like that. Okay. But I could give you one where you might have one of them is like 0 and one of them total formal charge might be like a minus 1. And then that would be one that might be more obvious. You might have one where it adds up to minus 1 and like minus 2. The -1 would be the more preferred charge.
So
So
whichever one's closest to 0 would have to be the
yes.
preferred. Okay.
Now, if they both add up to 0, but one of them has bigger numbers to do it, then that one will not be the preferred. Okay. All right. Those are great questions. Now, so that's how we do formal charge today. And so any other questions about formal charge for the time being? Okay.